Donc, nous avons le plaisir aujourd'hui d'avoir comme conférencier Matthias Weidemuller. Matthias connaît notre groupe et notre laboratoire depuis longtemps puisqu'il a fait son diplôme il y a presque 25 ans au laboratoire Caster-Brossel. Il a passé un an chez nous. Il a appris très bien le français, même si son séminaire va être en anglais, si j'ai bien compris. Donc il aurait pu le faire en français, je crois. Et donc Matthias, après son diplôme chez nous, a été faire sa thèse chez Ted Hensch à Munich. Je pense dans les années 90-95. Et ensuite, il a été à Amsterdam pour un postdoc chez Valraven, avant de revenir en Allemagne et donc de prendre une position à Heidelberg, à l'Université de Heidelberg. Et donc, il avait commencé sur les atomes de Rydberg chez nous, je crois, dans les années 90. Et ensuite, il s'est vraiment spécialisé dans les atomes de Rydberg. Et il va nous parler donc de physique dans des atomes, des gaz ultra-froids d'atomes de Rydberg. Donc, je lui laisse la parole. Matthias.
Yeah. Thank you, Serge. Merci. Je vais parler en anglais parce que c'est plus simple pour moi de donner des séminaires en anglais qu'en français. Donc, first of all, for me, this is an interesting travel into history because I was here about, as Serge said, about 25 years ago. I think the seminar or the courses were not given in this hall. It is more fancy, this hall, actually, than the one that we were in. But I remember that as a young student, we were following the classes of Claude Contanucci. At that time, laser cooling was a big topic. That I remember was one class, and the other class was on adiabatic coherent processes, so velocity selective coherent population trapping. So this was all inspiring us, and in particular, of course, also the time that I spent in Serge's lab. My love to Rydberg atoms has actually been ignited in this lab. And ever since, or not ever since, I should say, I restarted taking up these kind of activities like a little bit more than 10 years ago. And one of the things that also Serge taught us was try to start with simple systems, try to make them simple in order that you can understand them, but then also add enough complexity in such a way that you can also still understand it, but that there is enough complexity to make these systems interesting. And what I would like to present to you today is some experiments, actually quite recent work, that is going along these lines, and actually for those who attended the course before, it will line up very nicely to what Serge was alluding to, in particular, how interactions affect the energy transfer in these kind of ultra-cold Rydberg systems. So the goal of these kind of experiments that I'm going to present to you is that we want to realize a synthetic quantum system that allows us to study classical and quantum transport. So transport is actually one of the major elements of, if you want to transport the energy in nature, you can either do this by transporting charges, currents, and things like this, but if you have no currents, the only way to transport energy is to do by dipolar coupling. And there's lots of manifestations in nature for this dipolar transport, and there's many also questions that are related to this which are still unanswered. It relates to the question of the nature of random walks. It relates to the question of glass physics and spin glasses, and at the end of my talk I will show to you how you can nicely map also these Rydberg systems to spin systems. We created this is very recent actually, we created a very simple model for this. One of the things that actually also sparked some interest is the relation of dipolar mediated transport to photosynthesis. So this is one of these famous FMO light harvesting complexes. What they do is they collect a photon here, and this photon, the energy is absorbed by exciting some big complex here. What is completely removed here is this enormous proton scaffold that is relating this thing and sloppy, making a great environment. But then this energy is somehow magically transferred to some reaction center here where it's transformed into chemical energy. And the big question is why this process is so extremely efficient. So this process occurs with almost unity efficiency. And so far, nobody understands really why. There's still ongoing research in this direction. Some people claim that they understand it in terms of classical transport, where the where this energy is just classically hopping from one big aggregate to the next aggregate. But there has also been reports where people claim to have seen that these systems are actually showing a quantum mechanical behavior, delocalized wave functions, and even entanglement is being claimed to be seen. This is all ongoing open discussion, and the question is, can we learn something by using our beloved simple systems, super simple systems, about these kind of very complex systems, which in particular are coupled, where the system is coupled to large environments. So the question is, when is the transport governed by quantum mechanics and when by classical mechanics? What is the role of disorder correlations? Can we find other transport mechanisms that are mediated by additional degrees of freedoms? For example, Vironic coupling in the case of these large aggregates here. What about the nature of exciton-exciton interactions in large systems? And what does the environment, which role does the environment play? I mean, this is of course the open question all the time when we go from simple to more complex systems. And here Paris is of course the right place to address these kind of questions. Okay, so what I would like to show to you, and I can be rather brief in some parts, is if we think about creating a synthetic system, what are the building blocks? It will be Rydberg atoms in order to represent these spin systems. We will need this strong dipolar coupling, exactly the interactions that were explained in the course just preceding here the seminar, these Rydberg interactions. What is interesting in these systems is that even if you have a non-ordered system, there's an emergent length scale, and this length scale is due to the blockade. That was probably explained also here in the lectures before. And what I would like to show to you is that using EIT, electromagnetically induced transparency, you can even shape a controllable decoherence in this system. So, and then I will give you some little historical overview of what has been done in energy transport in ultracold Rydberg gases so far. I will show to you a technique that we developed in order to see actually almost now single Rydberg atoms using interaction-enhanced optical imaging. And this led us to in situ observe dipole-mediated energy transport in these systems. And I will show to you then in the end how we can understand this kind of dynamics by using some spin models which involve also the coupling to this, I would say, controllable environment. Okay, so I can be very brief here. I don't need to explain what Rydberg atoms are. What is important is, in particular for an experimentalist, is if you go high enough in principal quantum number, everything looks like hydrogen, and hydrogen we can understand well. So we can choose the atoms that we like most. In our case, it's rubidium, because we can manipulate rubidium very nicely, cool it, trap it, and even create quantum degenerate gases with it. I also don't need to show these scalings because they have just been shown in the course here at the end of Serge's course. And what is important for us, of course, is in the context of these interactions is this enormous scaling of the polarizability with the 7th power of the principal quantum number, which leads to these strong interaction effects. And they are nicely presented here in this graph, which I took from this review by Mark Sefman, Thad Walker, and Klaus Möllmer some years ago, which show at a certain distance scale here of 10 microns how the different interactions between neutral particles and ions scale. So here the interaction energy is given in hertz. This is 10 to the minus 9, and this is now always 4 orders of magnitude increase in the interactions. And you can, of course, see that if you take ground state atoms, the van der Waals interaction between ground state atoms can be completely ignored on this level. Even if I go now for magnetic dipole-dipole interactions, they are much smaller than the interactions that we typically encounter when we go to Rydberg states. Here, this would be for Rydberg state around 112 orders of magnitude increase. And what you also see nicely, and this has been also explained just in the lecture before, is there is this crossover between the van der Waals type interaction to resonant dipole-dipole interaction if I just change the distance. So this is an important control parameter. The other control parameter, of course, is the principal quantum number. So there's this enormous scaling of the van der Waals interaction by n to the 11th, for example. So I can change the principal quantum number. This allows me to change the interaction quite dramatically. And there's another tuning knob. This is electric fields, which can allow me to dial into further resonances and therefore also change the nature and the strength of the interactions by going from van der Waals to resonant dipole-dipole interactions. So there's the scalings again. We saw them also in the lecture before, n to the 11th for the van der Waals interactions, and n to the 4th if we go to the Förster-like dipole-dipole interactions. So some numbers, also some orders of magnitude. So typically we are in a regime where the electron wave function is still localized to one atom, so they don't overlap. And the distances between the atoms are typically in the micron scale. The lifetimes are of the order of 100 microseconds. So for all things that I'm discussing today, we can assume that this Rydberg state is stable because all the dynamics happens on much faster time scales. And what is important here is that the interaction energies, here now measured in hertz, are of the order of 10 to the 6 to 10 to the 9 hertz, megahertz to gigahertz, which is much, much larger than the thermal energies. And therefore also in all what I'm presenting today, I'm assuming that these atoms are actually stationary, that they are frozen. But we all know that there's effects that are related to actually mechanical forces that are also associated with these strong interactions. But we will now concentrate on the regime where all the dynamics is much faster than the typical time scale of these kind of collisions that are induced by the Rydberg-Rydberg interactions. Okay, so one of the things that are featured by this interaction is, of course, this excitation blockade, and I can also be very brief in this, but we will need this. As I said, this provides us with an emerging length scale in this system. This blockade is induced by the fact that if I have a pair of Rydberg atoms, they interact strongly. If I take S states, it's always repulsive in the case of rubidium. And therefore, what we see is within a certain critical distance, I cannot excite a pair. Only if I'm beyond this distance, the pair excitation probability gets up. And this is sometimes depicted in this kind of super atom picture where you have where you actually get back to an effective two-level system. But now the two-level system consists of a many-body system where within this many atoms there's only one single delocalized Rydberg excitation. And this goes along with this entangled state here, if you like, and there's an effective Rabi frequency for this system, which is then increased by square root of n. I have just one single excitation, but I have a square root of n enhanced dynamics. And this has been observed now in various experiments here in the Paris region, but as well as in other groups. So there is this kind of blockade, and one, let's say, variant of this theme and of this blockade theme is something that has been first introduced in the Rydberg field by Charles Adams. This is to use electromagnetically induced transparency. So this is like also already 30 years ago. That was the time when the quantum optics guys, they actually discovered the third level, and then they found that with the third level there's interesting physics that you can do beyond two-level systems. And the idea is the following. So you take a ground state, the Rydberg state. We assume, as I said, that the Rydberg state is stable. And we couple strongly this Rydberg state to an intermediate state. The coupling is denoted here by capital omega. We have a weak coupling then here to this ground state, and for all purposes that we are discussing here, this will be the typical first excited state transition in rubidium. So it's a nice transition with a large optical cross-section, and we can do absorption imaging on this transition, and we can excite atoms on this transition because we have a rather large scattering rate due to this intermediate state. But as Serge also already pointed out at the end of his lecture, there is this dark state that is emerging in the system, and together with quantum interference, what you have is a situation in this two-photon, three-level system that you never ever, if you're on resonance here, populate this intermediate excited state. So you turn down this de-excitation here, so you control the coupling to the environment in a certain sense. You turn off the fast decay, and at the same time the atoms now populate a dark state, which is a superposition of the ground state and this Rydberg state. And if we have the situation that this frequency is large compared to this frequency, this is essentially the ground state, and it's dressed by Rydberg character. And you can already imagine that this is a nice situation because now I can deal with ground state atoms, which are usually very weakly interacting, but now I'm dressing the Rydberg character, and therefore I'm also dressing the Rydberg interactions to these atoms. And I can do this in a controlled way because I have a control parameter here, which is this kind of coupling frequency. So this is the idea. And then one of the effects is if I look at the absorption of this light here, even if I have a completely optical intransparent medium, I can render it transparent by turning on this laser here, and on resonance everything is actually fully transparent, even if it's optically thick. What is interesting now is once I have another atom close by and I have interactions between these Rydberg atoms, then what it does, it actually shifts this kind of transition out of resonance, and therefore it also shifts this dark resonance to another position. And therefore, if my laser is still on this position, the presence of another atom here will change the absorption properties of this system. So it's no longer dark, you're no longer in this dark state, you start to scatter now photons on this first transition. So you can change the scattering properties of an atom by having another Rydberg atom being close by. You change the scattering properties of the ground state by having another Rydberg atom close by, and you do this because you have this dressing here. You have this dressing of the ground state with this Rydberg state. So this is actually the basic idea behind most of the things that I'm going to tell you today. So one of the effects, and this is something that Serge will discuss in his lecture in the forthcoming weeks, is that, of course, you not only address Rydberg character to give Rydberg character to the ground states, but you also change the properties of the light field. So what you do is, if you have a stream of photons going in here under EIT conditions, what you produce is dark state polaritons, or spin waves as they are sometimes called. But now these spin waves, they start to interact, and you get the same process, you get the same kind of blockade effects as they would have for Rydberg atoms, because you now also, these photons acquire Rydberg character, so you render these photons weakly interacting or even strongly interacting. This creates an enormous nonlinearity here in this medium, and what it also creates is non-classical light, because you can only enter one photon at a time. If there's a second photon entering, there's this blockade effect, and a second photon cannot enter until the first photon has actually left, or there's insufficient overlap between the ones. So there's now a whole list of different work that has been done in these directions. One of the things that we also did quite recently was we studied now the statistics of these dark state polaritons, and we also found that depending now on the atomic density, here measured now in terms of the Mandel Q parameter telling you how Poissonian your distribution is, we saw that by increasing the density we go from a Poissonian distribution where the Mandel parameter is 0 down to sub-Poissonian distribution when we go to the regime where we create these strongly interacting polaritons. And the picture behind it is that at low densities what we create is just polaritons which are reflecting the statistics of the incoming coherent light field, so therefore they are Poissonian. And actually I tell you, in such an experiment it's easier to find sub-Poissonian statistics than to find Poissonian statistics, because there's lots of artificial effects that can also create sub-Poissonian statistics. So the most important thing usually is to find this, to first show that you can find this Poissonian statistics. And then we see this decrease, which is consistent then with the picture of these hard spheres where I have these little bubbles sitting there. In this case, it's polariton bubbles, and each of them occupies a certain amount of space, and I cannot pack more than a certain amount of bubbles, photons, polaritons into this medium. And due to all these kind of interesting possibilities that you have with these Rydberg atoms and their interactions, this field has really exploded. It started with, as I will show, with energy transport, this field of cold Rydberg gases, but now it's touching many, many areas of research. You have heard last week by Tilman Pfau about the relation of this Rydberg physics to few body physics, so molecules, and then going even higher and higher, even to more or less electrons interacting with a bath of many, many ground state atoms. There is relations to correlated many body physics. This is what Serge is going to touch in this class next week or the week after. No, not after the break. There's relations to quantum phase transitions, spin systems, quantum information processing, this quantum optics I just mentioned briefly here, and this field here of energy and charge transport. This is something that is now currently also taking up speed. Okay, so what I would like to tell you now is what kind of experiments have been done so far on this kind of energy transport and what is actually meant by it. So the idea is the following. What we have is a system here where we create one, let's say, impurity, one excitation, we store one single excitation in this, what we call a state S prime, let's say, and now we want to watch how this excitation is propagating over such a system of other atoms in different states. So one of the possible implementations is that I take atoms of this kind here. So this might be a Rydberg state. I start with the Rydberg state here. This is my impurity. And then there's other Rydberg states in the vicinity. Let's call them S here. There might be an intermediate state which will allow you to, as I said, to tune the efficient coupling going from a van der Waals to a 1 over R6 or going to efficient dipolar couplings. So you can describe the system as having a coupling between S prime, either via this intermediate state PP, and this might be detuned or might be on resonance, and this can lead to a dramatic change in the strength and the character of the interactions, as I mentioned earlier. So actually, this has been already observed, these kind of processes, as was also mentioned, in many, many years before, and they were the starting point, I would say, of this field of cold Rydberg gases. Actually, Tom Gallagher, who studied these things in hot gases, was the first to then also see that there might be interesting applications with cold gases. But if you want to study these kind of systems in more detail, I think the best approach is, like always, is to somehow visualize the dynamics. So one of the things we would like to do is spatially resolve these excited atoms. So here's just a cartoon movie to what you would expect. This is really the most simple situation. This is just a chain here of these kind of atoms, and I assume that I have an excitation being presented here. At the beginning of this chain, they are all dipolar coupled, and then what we can see is, if we now turn this on, what we see is that this excitation is now just propagating to the left, to the right, and then back to the right on this chain. So this is, in solid state physics, this is the simplest realization of what you would call a Frankel exciton. That's this kind of quasi-particle that then moves over this chain and comes back. And what is interesting here, in contrast to solid state physics, and this is one of the great things of dealing with Rydberg atoms, the time scales now are on a time scale that you can easily observe. So we are now talking about microsecond time scales here. So we can observe these things in real time. Here, this is the situation when we have a disordered sample, and of course, if you have a disordered sample, what happens now? The distances are different, and so there are some systems which are at close distance which have a very fast dynamics where the excitation is exchanged very fast, and over other systems, over other atoms which are further apart, it takes longer times. But at the end, what you will have is a situation, if you have no decoherence, where this excitation in this quantum mechanics system will be completely delocalized. So you have a system now where this single excitation is, if you want, you may call this entanglement, but I don't know whether it serves for anything, where this excitation is completely delocalized over a large bunch of atoms, as long as there's no decoherence. So now the question is, can one see signatures of these kind of processes? And as I mentioned, it was Tom Gallagher and at the same time then also Pierre Piet and his co-workers in 1998 that studied these kind of energy exchange processes. At that time, the intention was to study first energy transfer and to see how this first energy resonance line gets narrower and narrower once I go to lower and lower velocities. So we saw this formula actually also in the lecture today, this formula where you can see the lower you go in velocity of the atoms, the narrower this first resonance should actually get. And to the surprise at that time, what happened is that instead of getting narrower, this first resonance got broader and broader. In particular, when you increase the density, you achieve resonances in now where the first resonance, which is usually measured in terms of a field, transformed into frequencies, is as broad as tens of hundreds even of megahertz, where you would expect at these situations, if you just had a two-atom system, you would expect a few megahertz. So, and the interpretation at that time was, what actually happens is that you create a single excitation, and then now this excitation starts to migrate out, which frees this first pair that was first undergoing this first process to a subsequent first process, and like this you can build up more and more excitations in the system, and you broaden the line, creating more or less a continuum in your excitation spectrum. Yeah? So that was actually the first observation, and I think it's fair to say that this somehow also started this field of cold Rydberg gases, because these were the first experiments that were using cold atoms in combination with Rydberg physics. We also did some investigations where we tried to do time-resolved energy transport. So we tried to time-resolve this kind of Furser process. The intention was to find out whether we can see any kind of signatures of this coherent energy transport, of this coherence in this kind of energy transport. But as it turns out, due to the fact that the atoms are not localized and that the atoms are actually not distributed along a chain, but they are distributed in a disordered fashion, what you see is, if you average over all different realizations, what you see is that the emergence of this additional Rydberg state through this transport is actually not showing any kind of signs of coherent evolution. The only thing you would only see this if you could resolve 2 atoms at a time. If you go to 4, 6, 10, then the dynamics is always the same. So the only thing that we could see at that time, going from changing different densities, was that we also didn't find any signatures of decoherence processes except the major decoherence process, which is the lifetime of the excited state, actually. So there has been also later experiments here. This is an experiment by Ben van Linden van der Heuvel and his group, Bart Noordam in Amsterdam, where they did now an experiment where they did first steps towards spatially resolving this energy transport. So the idea was you take 2 different optical tweezers here where you trap atoms, but now you trap these atoms and you excite them to 2 different states. So this is a 49 state here, and this is a 41 principal quantum number state. And the signature of this energy transport is then that despite having 2 different spatially separated clouds here in 2 different states, you suddenly see the emergence of different states, 49 and 42, which can only occur because these 2 clouds, these 2 spatially separated clouds, they start to interact via the dipole-dipole interaction. And they saw signatures that actually these states emerge, and even if they put these 2 clouds apart by several tens of microns, they still saw that this energy transport was actually occurring. So they saw kind of a first signature of this spatially resolved kind of transport. This is a very recent experiment here by Charles Adams's group. What they do now is they combine this electromagnetically induced transparency with this kind of energy transport by creating, using additional microwaves, these kind of excitons, which are now superposition states between 2 Rydberg states. And they look now, and what they found is that indeed they also see that there's a propagation dynamics. Indirectly they see this, and that there's also an emergent scale which is due to the blockade. So this is quite recent work. And there has been theoretical work. This is a work that I did when I was at the University of Freiburg together with a group from polymer physics, actually. They also found these Rydberg systems interesting. And one of the questions that was commonly raised in polymer physics and other fields of soft condensed matter is the question, can one decide between classical and quantum random walks, in particular if I have systems where there's trapping sites? And this is very much similar to now these systems that I was showing to you, these light harvesting complexes. So you assume that you have a chain of dipolar coupled systems, and you have one trap site which can actually absorb or trap the excitation depending. You can now let this trap site, you can also tune its decay and things like this. And it turned out that you can map this nicely on Rydberg states, and then following these calculations, one can show that with such a model, one can actually distinguish continuous time classical random walks from continuous time quantum walks. So that was also another motivation to actually start to do experiments along these lines. This is a theoretical proposal by Jan Michael Ross's group at the Max Planck Institute for the Physics of Complex Systems in Dresden. What they do is they go one step beyond now. Instead of only looking at the transport of energy between the different Rydberg states, they also include the mechanical motion. I said that there's always, of course, mechanical forces going along with these very strong dipole-dipole interactions that you have among these Rydberg atoms. And it turns out if you now also take the center of mass, degree of freedom also into consideration, what you find is that then this Frankel exciton starts to move, but it moves a little bit in a fashion like what they call Newton's cradle. So the atoms, at the same time, they start to undergo energy exchange and they bump into each other, yeah, and they get repelled. and they create an interesting dynamics which is now entangling the center of mass motion with the internal degrees of freedom. Okay, so this is all things that one would like to see in the experiment. So the first thing that you need to do in order to see these kind of things in an experiment is, as I said, you have to find some way to actually see state resolved, see the Rydberg atoms. And this is a difficult task. But there has been quite some progress in the last years. There are several methods now which show that you can actually image or spatially resolve one way or another Rydberg atoms. One way is pretty straightforward. This has been shown by, this is the group of Georg Reitel in Michigan. So what they do is they just use field ionization of the Rydberg atoms, the typical detection method that you would always use in order to detect Rydberg atoms. And then these ions that are produced by the field ionization, they are just extracted by an electric field, and they are impinging on a spatially resolving detector like an electron microscope or like an ion microscope. In a field geometry like an ion microscope. So like this you can increase the spatial distance like in a microscope, and then you see single events here, and if you average over long times, what they actually managed to see was that there is, for example, a dipole blockade. So they could really see that there are certain areas where if there's one atom, there's no other atom. This they could see by averaging over many of these realizations. There's another experiment which is now using these atomic many-body microscopes that were developed in the group of Emanuel Bloch in München and Markus Greiner at Harvard. So this is to use ground state, to actually image the ground state atoms, but what you can do is now you can map the Rydberg excitation back to the ground state atoms and then image them. And by doing this and doing repetitive measurements, Emanuel Bloch and his group, what they could show that it indeed in the blockade regime emerges these typical first there's a typical blockade distance, and in a more recent experiment they could also show that you can now create adiabatically, you can create specific kind of crystals, 1, 2, 3, 4 atoms, Rydberg atoms, and that they form regular patterns once you ram adiabatically into the Rydberg manifold. There's other realizations for this imaging of Rydberg atoms also quite recently, which use now not single electron systems but 2 electron systems. If you use a 2 electron system, you have a Rydberg atom, but you still have the inner electron that you can address, and you can now use this inner electron either to do laser-induced fluorescence. That's one possibility. So you really do laser-induced fluorescence now on the inner electron. It's destructive, but you can see then single Rydberg atoms here on the screen. Or you use auto-ionization due to this 2 electron system, and you then scan a laser and you scan this auto-ionization signal, which also provides you with a spatially resolved distribution of your Rydberg atoms. To study transport, in the first place, probably these methods are not so well suited because they are destructive. So at the moment you take the image, the dynamics has stopped. So you interrupt the dynamics. But they might be interesting to be used to study, to take snapshots of this dynamics. So what we came up with was an approach which allows us to actually follow the dynamics in real time. And this is again based on this idea that I was already alluding to, this idea that you can map Rydberg character onto the ground state atoms. And this you can do by this EIT imaging. And as I said, what you can do then, having another atom close by, you can shift out this resonance. And so the idea then is quite simple. You take some Rydberg impurities somewhere in your gas. They are embedded in a gas of ground state atoms. And now what you do is you do electromagnetically induced transparency on these probe atoms. So the great advantage is you don't populate this the population of this Rydberg state here of the probe atoms is negligible, so therefore it will not, in the first order, not influence any dynamics on the impurities. And in the second time, you can have lots of probe atoms that are actually influenced by one single impurity. So you have a transistor effect. So the absorption of 10 or 100 atoms is influenced by the presence of one single impurity. So this is then the idea. So you do a EIT on these probe atoms. When there's no impurity present, they will be transparent due to electromagnetically induced transparency. But if there's an impurity somewhere around, these atoms will be rendered intransparent again, absorptive. Yeah? So therefore, they will cast a shadow if you do an imaging here, like you would usually do in these cold gas experiments. They will cast a shadow on your camera. So each of these impurities now influences a whole bunch of ground state atoms, and this is again due to the fact that we have this blockade. So there's a certain length scale here, which is given by this blockade radius. The interaction strength enters and the coupling to this excited state, and this provides you with a length scale. This provides you with this bubble to within the absorption of these probe atoms is modified by the presence of this impurity. Okay, so it should be single atom sensitive and it should be non-destructive. So we first did some calculations where indeed if we now assume that we have an ordered structure, for example, of these Rydberg atoms created by also adiabatic sweeping into the Rydberg manifold, we would indeed, on paper at least at that time, be able to resolve this here as little spots in the change of the absorption of our imaging system. This included all kinds of noise sources that you could typically envisage. So, okay, but as an experimentalist, it's not good to rely too much upon proposals. So therefore, we set up an experiment to actually do this. This is how the experiment looks like in principle. So what we do is we trap atoms in an optical dipole trap, just an optical tweezers. We can field ionize them so that we can also measure the number of Rydberg atoms in order to calibrate the whole system. And then we have this counter-propagating coupling laser, which is driving this upper transition. And we have an absorption laser, which is then imaged onto a CCD camera, which provides us with the absorption images. So this is how the experiment actually looks like. There's a main chamber where we do all the experiments, and this whole thing is loaded from a two-dimensional magneto-optical trap with large loading fluxes. Inside, what is important is that we have, as I said, we have these Rydberg detectors, either a microchannel plate or a channeltron, and we have several field plates which allow us to control the direction and the strength of a field, either for field ionization or for tuning into first resonances and so forth. And due to this large loading flux and this dipole approach, if we want, we can create every 5 seconds, we can create a Bose-Einstein condensate. But the densities that we have in Bose-Einstein condensates, at least for the experiments that we are doing here, they are far too large. So all the experiments that I'm showing today are made in the regime where the densities are much lower than Bose-Einstein condensation. So how does the experiment now look like? What we do is we take now, as a probe state, we do this EIT on the 37S state. The impurity state that we prepare first is a 38S state, and they couple to this intermediate resonance state 37P, 37P. So again here, this is how schematically the experiment looks like. We have this probe beam, and then there's this coupling beam counter-propagating, which cuts out, or which is only illuminating a small portion of the cloud. So what we first do then for a few microseconds, we create the impurities, and then we shine in this EIT laser to probe what we have done. And so what you see is this is now a normal absorption image of a part of the atomic cloud that we have. This is this dipole trap. And then when we turn on this coupling laser, this is a little bit elliptical shaped here, this laser, you see that in the center of this cloud now we render the absorption transparent through this electromagnetically induced transparency. And then there is this impurity region, and actually the impurity region is smaller, much smaller than the region of this coupling laser. So the sequence is then like this. We take an EIT image, so this is this image here with EIT laser. We now create the impurities, so you can already see that by the impurities the absorption is drastically changed here in the position where the impurities are produced. And just by taking now the difference between the two pictures, we can actually see the absorption, or we see the signature, the optical absorption change due to this cloud of Rydberg atoms. So this is how it works, and there's a certain regime in which it works best. So this is the absorption here. This would be the EIT absorption. It also changes with density because of the interaction of the polaritons and this EIT phenomenon. This would be the two-level absorption increasing with density, and then there's this window between the two where you can best do this EIT plus impurity imaging. So there's a window of densities where it actually works best. So we have 5% impurity atoms. In this experiment, we had 300 Rydberg impurities. which were influencing 3,000 absorbers. So there was 10 additional Rydberg, 10 probe atoms sensing one single, on average, sensing one single Rydberg atom. So the time resolution is 2 microseconds that we can achieve with this method, and it has a single shot sensitivity. So in principle, we can take these pictures with single shot. What is also nice using now Förster resonances, we can even tune this kind of number of absorbers or the sensitivity of the system. So this is the Förster defect here, and you can see that the additional absorbers can be changed by a factor of 5 or so by just tuning this interaction between the probe and the impurity atoms through a Förster resonance. This is a measurement now where we tried to go as far down as we could at this experiment that we had at that time. So that was here a single shot image of 6 impurities here. Typically what we have is then 20 atoms sensing one impurity. Then we did a move. Yeah, I hear that you're also moving. We did a move, and since then the experiment improved. Now we are currently at 2 absorbers, and we are still working on the camera signal to noise analysis, and I think we will soon get down to a single Rydberg atom resolution. So what we saw then, and I tell this story now in a nice coherent way, but it, of course, like always in experimental physics, it was not like that. What we wanted to actually show was this imaging method. What we found was transport. Yeah? And this is one of the nice things of doing experimental physics. You start something and you get something extra sometimes. Sometimes you start something and you get nothing. But here, you start something and you get something extra. And what we saw was indeed that I wanted to study transport, but I never had this method on the agenda, actually, I should say. But what we saw was indeed that this cloud that we observed now was starting to increase. So first we thought this cloud is just increasing because the atoms are moving. So we did a test experiment where we turned off the imaging and just shot an image at the end of the sequence instead of illuminating the gas all the time. And there we saw that indeed the atoms don't move. So it's no mechanical movement that happens here. It's not just expansion of the cloud. The cloud is really frozen on this time scale that I was mentioning here, a few microseconds. But what happens, or what diffuses, is the Rydberg excitation. So it's really this energy transport now that we can see here. So we studied this more quantitatively. This is this test experiment where nothing moves, and here this is the experiment where we illuminate the atom at the same time, the probe atoms, and at the same time we see how this excitation of the impurities starts to propagate, and it turns out that it follows a classical diffusion law. So the size of the cloud increases with the square root of the time. So we try to understand that, and we measured a diffusion constant, and we now had to set up a model in order to understand what's actually going on in this experiment. So now the picture is the following, and what we have is we have these impurities here, all of them sitting here. Around them is this sphere. To within they change the absorption properties and the scattering properties of the surrounding ground state atoms. And around them, there's also permanent, a whole gas now of atoms which are dressed by Rydberg states, because we're doing EIT on all of these atoms. So all of these atoms around here, they are dressed by a little bit of Rydberg character, and there's these impurities in the center, and in the middle, or in the ones that are sitting within the sphere, the probe atoms, these probe atoms, they scatter light because the EIT condition has been broken. Yeah? So what is the times, or what is the important scales here? So one of the things that we can immediately see is that the probability of finding a probe atom in a Rydberg state is increasing spatially in this manner here because of the blockade. So if I have an atom within this impurity, this probe atom will scatter photons on the first transition because EIT condition is broken. Therefore, this atom will have no probability of being in the Rydberg state. This is why this goes down here, the probability of finding these probe atoms in a Rydberg state. Whereas if I go outside this blockade sphere, these atoms undergo usual EIT, and due to the admixture of the Rydberg state, they have a certain probability of being in the Rydberg state. So now I can guess what the probability of energy transfer is from this impurity atom to one of the probe atoms. This I can guess by just seeing that should go down to 0 if I go to small distance. This is because there's no partners available for energy hopping. And it will drop off by a 1 over R3 law if I go outside. So therefore, what you will see is a function that is peaked by at a distance, and this distance, as it turns out, is exactly this blockade radius. We first were a little bit puzzled based on the simple model, but as I will show you in a few minutes, you can back this up by a more quantitative model. Okay, so there's a preferred hopping distance, which is given by this blocking radius, and this was this emerging scale that I was alluding to in the beginning. So then there's another important factor, and this is that we are permanently probing the position of this excitation. We are probing this position of the excitation by scattering photons from the atoms that are in the vicinity of this impurity atom. So there's another rate here, and this is this environmental decoherence rate, which you can actually change. But it's a decay rate which is a collective rate due to the fact that there's many, many atoms in the vicinity of this impurity, and they can therefore sense the position of the excitation. So now one has to see how these rates they are relative to each other, and it turns out that this environmental decoherence rate is larger than this hopping rate, and what you then have is that you end up with a continuous projection on this quantum state with a hopping rate now given by the square of this coherent rate divided by the incoherent rate. So like you always have in systems that are coupled to a reservoir, coherently driven systems coupled to a reservoir. So if you take this now together with this preferred hopping distance, you can derive a simple diffusion coefficient, and if you look at the numbers, they fit at least in their order of magnitude. So it seems that this simple model captures the essential physics of what's going on. So what you have is you have an environmental induced hopping, or you have a hopping due to dipole-dipole interaction where the environment actually induces decoherence and makes this process becoming a classical diffusion. And the environment is presented by these atoms that are in the vicinity of this impurity. Okay, so this was at that time a rather hand-waving model. Meanwhile, we have worked this out in a little bit more detail, and this I would like to show to you in the remaining few minutes, how we can map this on spin models. And it was actually Shannon Whitlock in my group that did this kind of investigations quite recently. So the idea is that you would like to map this now on spin models that are also used in other areas of physics, where you have a spin here and you wonder how this spin is actually propagating, or the spin excitation is propagating over a larger array. So in our case, what we have is this Rydberg impurity, and this is coupled now to a whole bunch of Rydberg-dressed ground state atoms. So as I said, we map this Rydberg excitation on the ground state. You have seen this picture now for the third time. And what we can now assign to the system is something like an effective spin. We have these two Rydberg states, let's call them S and P. They are coupled via this dipole-dipole interaction, going with 1 over R3. And in addition, what we have is we have this EIT driving on this SG transition via this intermediate state E, and this intermediate state can decay by a fast decay rate gamma. And due to the fact that we have these different coupling strengths here, we can tune all these we can tune the mixture of the ground state and this Rydberg state by just changing the relative ratio between this coherent coupling omega and kappa here. So what we have then is a dipole-dipole coupling between these Rydberg states. So we can transform this two-atom picture into a pair picture now, where we have pairs of ground state and P state, ground state and P state, and here this would be ground state. This would be PS pairs. What you see is these are coupled here via this coherent coupling, and there's the dipole-dipole coupling, which couples an atom in the PS with the pair being in the SP combination. So this is just another way to show it. And now there's a nice feature. If you now go into the regime where you have into this EIT regime, what you can do is you can adiabatically eliminate this state S, because it's barely populated. It has a very small population. And you can also eliminate this intermediate state E, because it's also hardly populated under the conditions of strong driving on this transition omega. So what happens is that the EIT dynamics actually follow adiabatically, and what you end up with is an efficient hopping or coupling strength between this combination of the ground state and the p state and the ground state and the p state. And this is your spin system now. So now you have realized a very simple spin system. Now the spin is mapped by this p state and this ground state. So what can you do with this? What you can then formulate is a master equation. There's the coherent dynamics here, and you have this Lindblad operator, which describes the coupling to the reservoir. And what is nice is there's a recent paper by Anders Sørensen and co-worker that you can now, once your operator has a certain structure, your Lindblad operator, and it turns out that our system exactly has this structure. That was the surprise that we found. Then what you can end up with is an effective Hamiltonian, where you have this effective hopping rate here, coupling your spins, and you have two efficient decoherence rates that emerge out of the system. One is incoherent hopping, given by this parameter gamma effective. So this is just also changing hopping of the spin or the excitation from one to the other, but with this effective incoherent rate here. And there is an irreversible dephasing, which means a decay of your state, where one atom is in the ground state and the other atom is in the excited spin state. So you have two decoherence rates that emerge from this problem. And they can be written down in very simple form on two important parameters which determine the whole dynamics. One is the two-level atom scattering rate, just given by this coupling of the two-level system kappa squared divided by the decay of the intermediate excited state. And there is this other important parameter, is the interaction strength relative to the bandwidth of the electromagnetically induced transparency. So two very simple parameters. So this one determines the dynamics, and this one determines the strength of the interaction, or the relative strength of the interaction to the effective decay of the system. And these parameters are all tunable. That's the nice thing about it. So what you find then is, if you now map out the spatial dependence of the system for a pair of atoms, you find exactly the same picture that I showed you before from our hand-waving model. So there is this effective collective decay rate, which is having a maximum at small distances and decays to at larger distance. And the hopping rate itself, this effective hopping rate, it has a maximum at exactly the blockade radius. So you retrieve exactly this hand-waving model that I was using to explain our data from this from the spin model. And you can see that there's two regimes. There's the blockade regime at small distance, where the interaction with the system acts as a two-level system, more or less, which is distinct now from the coherent regime, where you have an effective hopping described by this simple formula here. So what is nice is you can now, by controlling the distance, for example, you can control the dissipation. So you have a knob on your dissipation or your coupling to an environment. So you can extend this model then to a model of n spins with one single excitation. And what you actually find then is an effective spin Hamiltonian for this system with these effective two decoherence terms that enter here for this system. And this is the last thing I would like to show you. What is then nice to see if you do now simulations on a disordered sample, that you, by having one single control parameter, you can actually enter three different regimes. And this is actually what our experiments are going to aim for in the next future. There's one regime where you have coherent transport. This is the situation where the dipole-dipole interaction is much smaller than this typical coherent driving rate. Then what you see is here the expansion of the wave packet, or the excitation. The excitation is actually spreading in a quasi, it's a wave function, but and this edges like quasi-ballistically. So you have this kind of quantum or coherent transport. If this parameter is of the order of 1, you find classical transport. Actually, it's exactly a square root of time dependence here of the expansion of your initial cloud. And what is interesting, if you now go to large coupling parameters, you see this emergent blockade, this emergent scale blockade dominate transport, where the hopping distance is defined by the blockade radius itself. So I think this is a very interesting system to now study these kind of transitions and to have a deeper look into spin models that find applications also in other systems in nature. Actually, we are currently working out to apply this spin model to now interacting spins. So far there's only one single excitation here, but you might also now extend this model to interacting excitons. So having 2 spins, for example, and then you can map these systems exactly to systems that were actually, this one you can map one-to-one to the systems that were recently studied by Junier, now not using Rydberg atoms, but using ground state molecules. It's actually exactly the same physics of what they are studying and what we are seeing here, down to the time scales. The difference is that the scaling time scale here is a different one in his experiments. It's more seconds. In our system here, it's microseconds. But the physics is really exactly the same. Okay, so what I showed to you is that now with all these methods that are available and all these possibilities to control interactions in Rydberg atoms, you have all these building blocks that you can use to actually study transport in a controlled way in these kind of systems. I showed to you that there's a way to actually see Rydberg atoms by optical absorption using interaction-enhanced imaging and the modification of absorption through the presence of impurities and the dressing of ground state atoms by Rydberg character. I showed to you that with this we could observe dipole-mediated energy transport now in the classical regime as the analysis shows. And I showed to you that you can now use models from spin physics to actually describe these systems and to extend this research also to systems where you can actually now study how the environment, for example, changes the character of the transport. Okay, let me also give credit to all the people working on this project. Shannon Whitlock is the second principal investigator on this project. Here you can see that we are also traumatized by moves. Yeah? Actually, I don't know how many moves I did already in the past, but this was the latest one here, April 2013. We moved the optical tables, moving from the Philosopher's Way into a building with a less mundane address. Yeah? So it's now the Neuenheimer Feld. Actually, I preferred the Philosopher's Way, but I couldn't get handle of this plate of the street. So we're still trying to get this there. So this was the move in 1 year ago. Shannon Whitlock, Georg Günther just finished his PhD thesis. Hannah is writing up her thesis. Christophe already moved to industry. Martin Robert de Saint-Vincent, he did very, very important contributions to this experiment. He recently moved to Oxford, but I just heard that he got a permanent position at CNRS quite soon. Thomas Kerst is a diploma student or master student. Vladislav and Miguel are the new PhD students on this experiment, and Stefan is the PhD student in a new project of Shannon Whitlock that has just been started in the framework of an Emmy-Noether group. And we have 2 guest visitors, Giulia Faraoni and Maria Valado. Giulia is doing her master thesis in my group, both coming from Ennio Arimondo's group, and Maria is doing a part of a PhD thesis in the framework of this European network coherence that we are running. So with this, I would like to stop and thank you for your attention.